start for the second part of the lecture. So I will jump a few years ahead. We were before the break in 1916, and now we jump to 1923. And again, another contribution of Einstein to the understanding of quanta. In fact, it happened quite by chance. Einstein received in 1923 a letter from a young Indian scientist, Bose, who was working in India, and Bose had calculated again in a different manner Planck's law. We have seen already two ways to find Planck's law: the way by quantizing the oscillators, the way by introducing stimulated emission. And Bose had another point of view. Bose took very seriously the idea of photons, and he said, okay, if the photons are particles like atoms, maybe I could retrieve Planck's law by doing the same kind of statistical arguments that Boltzmann did to find the law of gases using statistical mechanics. So can I use statistical principles to recover Planck's law? And he did that. He computed the entropy of a gas of photons by using a very special method to count the states, to count the photons. In fact, he assumed implicitly, without saying it clearly, he assumed that the photons were completely undistinguishable particles, which was not the way Boltzmann did. In fact, if you look at the gas theory of Boltzmann or Maxwell, the atoms in the theory are classical balls, classical particles. You can number the particles. You can give a number or a different color to each particle to individualize them. And for instance, if you have two configurations in which particle 1 is at point X and particle 2 is at point X prime, this configuration is different from the one in which particle 2 is X and particle 1 at XY. Boltzmann considered these two configurations as two possible configurations of the system. Of course, there is no way in a gas where you have billions and billions of atoms to follow each of them in practice. But this was not the problem for Boltzmann. He said, I don't care what is in practice. I could always imagine that there is a kind of daemon who take a snapshot of the gas at one moment. I give a name to each atom, and then I follow what happens to them. And if I do that, the particles will keep their individuality, and I could do this kind of calculation. What Bose assumed is that you cannot do that for photons. The situation in which one photon is here and the other is here is exactly the same as the reverse, and there is absolutely no way you can distinguish the two. And if you count in these two different ways, you find different statistics and you find different states for the gas. And I will try to explain that in a moment. But by doing that, Bose had discovered something very profound about quantum particles. And Einstein understood that immediately. In fact, Bose had tried to publish his paper, which was rejected by journals. And that's why, in an act of despair, he sent from India, he sent the article to Einstein. And Einstein immediately understood the interest of the paper and got it published. And then he thought about that, and he had more profound ideas that I would like to discuss with you in the remaining part of the lecture. So let's try to understand what's going on here. And I think the reason why Einstein was immediately caught by this idea is that what we will see is that when you use these statistics, assuming that the photons are completely undistinguishable, you find the result that the photons like to gather, like to be together, exactly in the same way as in stimulated emission. You see that the photons have a tendency to accumulate in the same mode. So Einstein immediately had the idea that Bose had hinted to something very interesting about the properties of photons and other kind of particles. But before that, I will make a digression to discuss this idea of indistinguishability. I take the simplest possible example. I assume that I have two particles and two boxes. For example, you have a gas, a room, and you separate it in two parts, and you try to find out whether the two particles are in the left part of the partition or in the right part or in the two parts at once. And on the left, I have assumed that I can distinguish the particles. And to distinguish them, I took two colors, red and blue. And you see immediately that you have four ways to distribute the particles if they are distinguishable. Either the two particles are at left, or the two particles are at right, or you have the blue at left and the red at right, or the opposite. Now, if you assume that the disorder is maximum, the entropy is maximum, that these four configurations have equal probabilities. And so the probabilities to have the two particles at left is 1/4. Now, if the particles, if you cannot distinguish the particles, that's what I have shown on the right part. I just put black circles. You see now that you have only three possibilities. Either the two particles are at left or they are at right, or one is at left or is at right. I don't know which. It doesn't make sense to know which one. And now the probability to have the two particles at left is not 1/4, it's 1/3. So you see that even in this very simple example, if you don't distinguish the particle, you favor more the configuration where the particles are together than you do in the other case. And this is true even with two particles. Now, if you take more particles, it becomes absolutely overwhelming. I assume if you have n particles instead of two, what is the probability to have all the particles on the left? It's 1/2 to the nth power, because you have probability 1/2 to have the first particle at left, then you multiply by 1/2 for the second, 1/2 for the third, up to the nth particle. So it's an exponential law. It's 1/2 to the nth power. What is the probability if the particles are undistinguishable? Then you have only n+1 possibility. Either you have one particle at left or two or three. And so the probability to have all the particles at left is 1/n+1. Now, 1/n+1 is small, but it's fantastically larger than 1/2 to the nth power. For example, if you have 30 particles, 1/2 to the 30th power is 1 billion. So you have the chance to have all the particles at left is 1 billionth if they are distinguishable, and it's only 1/30 if they are 1/31 if they are not. And you see that the probability to have all the particles on one side is enhanced by a factor of 30 million, even when the number of particles is small. But if you take now an Avogadro number of particles, then it's absolutely overwhelming. There's no possible comparison between the two numbers. So you see that by assuming that the particles are undistinguishable, you favor tremendously the configuration where the particles are together. And this is a property of particles called bosons, as I will explain in more details now. Now, a reminder about combinatory mathematics. I will need only one formula. What is the number of arrangements of n particles? By arrangements, I mean, what is the number of ordering of n particles? And of course, this is a number which is well known for mathematicians. It's called n factorial. Why? Because if you have n numbers and you have to arrange them in a given order, you have n ways to choose the first one. Then you have n-1 way to choose the second, n-2 ways to choose the third, and so on. So you get n factorial. And the factorial of n, which is not an n with a mark like that, it increases exponentially with n. And there is a formula which is called Stirling formula, which I will use a lot in the remaining of this talk, which says that n factorial is very closely equal to n over e to the nth power, where e is the Euler number, the basis of Napier logarithms. It's 2.71 to the nth power times square root of 2 pi n. And in a logarithmic form, you have log of n factorial is just very close to n log n minus n. and there is a correction which I will neglect. So it's a very big number of arrangement of n objects increase exponentially with n, and the logarithm is proportional to n log n, is nearly equal to n log n. So now I will ask a very simple question in combinatory mathematics. What is the number of ways to distribute n undistinguishable objects in G boxes? I assume that I have G boxes, and I want to put some particles in the first box, some in the second. How many ways I have to do that if the particles cannot be distinguished from each other? That is, I generalize what I have done with the two boxes of the first example. So the calculation is very simple. In fact, what you have to look at the arrangements in which you put the particles everywhere. In between, you have to put partitions to build your boxes. And so if you have G boxes, you need G-1 partitions to separate the volume into G parts. And I've shown it here. Here I have displayed as an example what happens when n is equal to 7. So you have 7 atoms or 7 photons, 7 particles, and 5 boxes. So for 5 boxes, I need 4 partitions. Now, the number of arrangements, if I don't care about whether it's atoms or partitions, the number of arrangements is factorial n plus G-1, because I have n plus G-1 objects. But now, if I do that, I have too many arrangements, because the order, whether I call my partition A, B, C, or D, or C, B, A, or D, or any kind of combination, it's the same result. So I have to divide this huge number by factorial G-1, because all permutation of the G-1 partitions will not change the distribution. And finally, if I cannot distinguish the atoms, I have also to divide by factorial n, by n factorial, because permutation of any of the n object will make no difference. So I find the result I was looking for. If I have to distribute n undistinguishable objects in G boxes, the number is n plus G-1 factorial divided by n factorial G-1 factorial. So that's the formula that Bose used in his statistical, in his calculation. So how did Bose do the calculation? He said, okay, some photons will have the energy E sub I, epsilon I. So I will label by the letter I an energy level, a given energy for the atom. And I assume that I have GI states which have the same energy, that this energy is degenerate. For example, if it's the kinetic energy, all the particles going in all kinds of directions with the same kinetic energy are degenerate. They have the same energy whether they go in this direction or that one. So you have a big number which represents the number of ways you can have the energy I. So GI is the degeneracy of the level. And you have n atoms. So the number of combinations, the number of available different states for this n objects in the GI, in the Ni object in GI boxes is given by this formula. And this is a huge number, of course. It's a huge number, but this is a number which measures the disorder in the system, because you don't know a given particle where it is. And this is something which is the formula which Boltzmann used to define the entropy. In fact, what Boltzmann used to define the entropy is a logarithm of this number, because this number is so huge that it's not useful directly, but it takes the logarithm. And in fact, what you have to do is to compute the number of possibility for each energy I. So you have to multiply all these W's by themselves. And when you take the logarithm, this product becomes a sum of the Stirling formula. Each of these huge number has the form n log n, and you have to sum over all the possibilities. So that's exactly what was done by Bose, and he derived the entropy of the photon gas. So I let you look at the formula. It's just taking the n factorial that I have on the left of the slide and use Stirling formula. Each of these factorial is n, the n log n minus n term. I get this. And then you have to maximize this entropy. The system will settle into the state which will have the maximum possible disorder. So maximize with respect to what? With respect to the NIs. You can change the NIs the way you want, because you have a gas of photons. Some photons may disappear, some photons may appear, because they interact with a thermostat at temperature T. They interact with a reservoir with atoms at temperature T, which can emit or absorb photons. So what you have to do is to differentiate this quantity to look at how S varies when the NIs varies by small amount. And this is what I have written at the bottom. You have to compute the delta of log W, and this is done just standard calculus. You know that the derivative of log x is 1 over x, and so you can do all this calculation. I let you do it, and what you find at the last line is the variation of this entropy. It's Boltzmann constant, sum over I of log Ni plus Gi over Ni times delta Ni. So this gives you the variation of the entropy. But do you want the entropy to be maximum? No, what you want is to have the free energy minimum. So you have to add to this the variation of the energy. And then you will compute E minus Ts, and you will look at the minimum of E minus Ts. So here I have computed Ts, or the variation of Ts. Now, what is the energy? The energy is very simple. It's sum over I of Ni epsilon I, where epsilon I is the energy of the ith state. So you have this quantity, and now you have to derivate this. The variation of the energy is just epsilon I times delta Ni. The variation of the entropy, I have given it to you on the previous slide. And now you have a quantity which has to be minimum for all possible variation of the delta Ni. That is, the term under bracket has to be equal to 0. The term under bracket is just epsilon I minus a logarithm. You take the exponential of both sides, and you can extract Ni. You find Ni equal to Gi over exponential epsilon I over kt minus 1. And you find again a term which reminds you very strongly Planck's law. In fact, it's exactly the term you have in Planck's law. So you got this result. Then the only thing which remains is to find what is Gi. Gi is a degeneracy of the state which has a given energy. And we know what it is. We have computed it before. That's the number of oscillators, the number of states which have an energy comprised between U and U plus du. That give you the number of states which have the same energy, which is a Gi in the formula. And then when you put everything together, you get Planck's law. So he got Planck's law by just assuming that the different configurations have to be computed by assuming that there is absolutely no way to distinguish between two photons. If Bose had used Boltzmann trick, if he had labeled the photons, he would have not found this law. So this vindicated him. It was a proof that he used the right statistics to describe photons. But in fact, this is not clear in Bose's paper. It was just he did the calculation without explaining very well how he did it. Einstein went much further, and he said, okay, but if you can do that with photons, why don't we do that with atoms? Why don't you have atoms which obey the same? After all, atoms are also objects which should be undistinguishable in some way. So Einstein took the same point of view, Bose's point of view, and he tried to rederive Boltzmann calculation for a gas, assuming that you could not distinguish the configuration in which you exchange atoms. And it was exactly the same calculation as Bose, with one exception. In Bose's calculation, the number of photons is not fixed. The number of photons can change. If you have atoms in a box which with walls around it, the number of atoms is fixed. You cannot, when you vary when you do this variation, which gives you the minimum of the free energy, you have to make sure that the number of atoms does not change. In other words, what you have to do is to minimize a function with a constraint, the constraint being that the sum of the delta ni should be 0. If one delta ni increases, another one should decrease to conserve the sum. And now what you have to do is to minimize a function with a constraint. We already had an example of that when we talked about the principle of least action. What you do when you have that is that you use the formalism of the Lagrange multipliers. Lagrange is the man who showed that the principle of least action was equivalent to Newton's law. And so he had the formalism to describe how you compute the external of a function when you have a constraint. And so what Einstein did was to use the same formula as Bose, but he added a term here which takes into account the fact that the sum of the delta ni cannot change. And he introduced this constant mu, which is called a Lagrange multiplier. So you solve with this mu that you don't know what mu is about. And when you finish the calculation, you compute mu by stating that the total number of atoms is a given number. And this will give you the way mu is obtained. So if you do that, then the calculation follows exactly like Bose, and you get now the distribution, the number of atoms having energy I is Gi, the degeneracy of this state, divided by this. So it's exactly Planck's law, except that instead of having epsilon I, you have epsilon I minus mu, where mu is this Lagrange multiplier. And it's called here the chemical potential. It's chemical potential, which I would tell you how you obtain it. So in the case of photons, mu is equal to 0, because the number of photons is not fixed. But for massive atoms, which behave like bosons, mu is a negative quantity. We will see that it's a negative quantity. So the particles which obey these statistics, whether they are massless particles like the photon or massive atoms, are called bosons in honor of Bose. In fact, Einstein did a lot of, was a very nice man because he gave credit to Bose. This is his discovery. And the idea is that you could have particles which obey the statistics, which are not just photons, but that is generalized to other kind of particles, was Einstein's idea. And so he studied this state, and he came to the conclusion that at low enough temperature, all the bosons should fall down to the ground state of the system. This is a phenomenon called Bose-Einstein Condensation. The fact that particles which obey the statistics will condensate in one state if they are massive and if their chemical potential is negative. So it's not a property of photon, but it's a property of a variety of atoms called bosons, bosonic atoms. And he made this discovery in 1923, and it took 72 years before Bose-Einstein condensation was really observed in the lab in 1995. So it's like the laser, it's kind of premonition by Einstein, which was in fact confirmed by experiments much, much later. So how did Einstein find that? Well, I start from this basic formula here. And of course, now how do you define mu? What you have to write is that the sum of all the Ni, which is capital N, is a total number of atoms. And this total number of atoms is fixed. So we have a sample with N atoms. So this is a boundary condition, is a constraint, which will give you the number of atoms. Einstein expressed this formula in this way. He introduced what is called the fugacity of the gas, which is just the exponential of mu over kT. And then when you do that, you find this formula, which is exactly the same as before, but this notation will be helpful to understand what's going on. And so you can compute Z by the implicit way to compute Z is to express this identity here. So then what Einstein did is to separate the ground state of the system from all the other states. And he assumed, and this is generally the case, that the ground state of the system, epsilon naught, you can always take it as 0. Take the origin of the energy for the ground state of the atoms, the atoms which have the least possible energy. You call this energy epsilon naught. And this state, he assumes that it was not degenerate, that G0 was equal to 1. For instance, if you have atoms, it will be in a potential well, atoms which cannot escape. The ground state of the system is just one state. So epsilon naught is equal to 0 and G naught is equal to 1. And you see now that if you do that, N naught is just equal, if you make epsilon naught equal to 0, this is 1. And so you find N naught is equal to Z over 1 minus Z. And you can extract Z. Z is equal to N naught over N naught plus 1. So from this formula, you see immediately that Z is smaller than 1. So Z is comprised between 0 and 1. And if Z is between 0 and 1, mu is negative because Z is e to the mu over kBt, so mu is negative. So chemical potential for bosons is negative, and Z is comprised between 0 and 1. Next step. So what you find that as T decreases, the number of N0 will increase. So Z is going to become closer and closer to 1. And if you separate, you can write N is equal to N naught plus the sum of all the other terms that you have in here. So the sum for all the I larger than 0 of the GI of Z over exponential minus Z. And you take this term, and so I need you to do the calculation. What I want to see is how this term is varying when Z is comprised between 0 and 1. And what you find that this term is smaller, is an increasing function of Z. So this term reaches its limit. This term reaches its limit for Z equal 1. You compute the derivation with respect to Z, and we'll find this result easily. So what it means that N minus N naught is smaller than this term when you make Z equal to 1 in it. So you see that what is N minus N naught? N minus N naught is the number of atoms that you have in the gas which are not in the ground state. So that's what is called the gas phase. So the number of atoms which are not in the ground state is bounded by this quantity. And this quantity does not depend on N. This quantity is a fixed number. You can compute it, and I will show how you compute it then. So you see that there is a maximum number in the gas, depending, of course, on the volume and the temperature. So there is a maximum number. It means that if you increase, if you want to put more atoms in the system, they cannot get in the gas. They have to go in the ground state. And this is what is called the Bose-Einstein condensation. The fact that you have the gas is saturated by a fixed number of atoms, which depend on the system, and all the other atoms have to go in the ground state. Now you can also look at the problem in a different way. Instead of considering that V and T are fixed and that you increase the number of atoms, experimentally, the situation is easier to consider. The other situation is easier to consider. Assume that you have a box. In the box, you have a given volume and a given number of atoms, which cannot change, but you decrease the temperature. So what you change is the temperature. And you look at this function, and you look at how this function varies when you decrease the temperature. Now you have to know how you compute this function. You have to make a sum over GI of this quantity. What is the sum over GI? The sum over GI, what are the energy states? The energy atoms which have a given energy have a given momentum, but the momentum can be in any direction. So the GI will have a term which is as for the photons in the Planck's law, we'll have 4 pi p squared dp. This is the volume in the momentum space comprised between p and p plus dp, because you have a sphere of radius p, you add dp, and you take the volume. And you have to count the number of states in this volume. And when you count the number of states of this volume, what the intuition Einstein had is to use as a unit cell h cube. Why? Because what you count is the number of states in phase space, p times x, which is homogeneous to an action. And so it's natural to take the cube of Planck's constant as a unit cell. And that's why you see that in this quantity, there is v over h cube. The number of states is proportional to the volume, and you divide by h cube, exactly in the same way as I divided by 2 pi over L cube when I counted the number of states in the photon distribution. So you do that. And of course, this was an intuition, but this intuition was confirmed 1 year later when De Broglie introduced the matter waves, because then the comparison between optics and atoms will become even clearer. But that's what Einstein did. And when he did that, he came to the result that N is given by this expression. This is an integral that you can compute. It contains a temperature. And what Einstein said is the critical temperature for which the Bose condensation starts is the one for which the right-hand side of this equation is equal to N, because then all the atoms, you cannot have more atoms in the gas phase. All the atoms will have to fall in the condensed phase. So after that, I don't want to enter into the details, but you use some mathematical tricks, and then you get, after some tricks, you get that N over V, which is the density of atoms, is given by this quantity. Tc is the critical temperature. So you have a relation between the temperature and the density, which is critical value to get the Bose-Einstein condensation. So I stop at this point, this thing. I just want to say that 70 years later, this was achieved, and the orders of magnitude are given here. The critical, the condensation has been observed with rubidium atoms, so you can put the mass of rubidium here. And typically, what you have are condensates, which you have 10 to the 5 to 10 to the 6, about 1 million or a few million atoms, in a volume of about a few micrometer cube. And the critical temperature is 10⁻⁷ Kelvin. So it's very, very, very cold. These are the coldest objects ever studied in the lab, and maybe the coldest objects in the universe. They are called Bose-Einstein Condensate. There is a lot of beautiful physics too, which is now being done with them. They have been discovered 26 years ago. And in this quarter of centuries, there are hundreds or thousands of groups in the world who are working on this condensate. And I will talk more about them when I will explain to you how you can get to this very low temperature, which is not obvious, 10⁻⁷ Kelvin. That's in a logarithmic scale. These temperatures are we at 300 Kelvin. We are closer to the temperature of the stars than the temperature of 10⁻⁷ Kelvin. This is 10 orders of magnitude lower temperatures than room temperature. So that's Bose-Einstein condensate. And you see here, I show you on the left part of the slide how the N naught over N, the fraction of condensate, when you decrease the temperature. So at threshold, you start to increase the number of atoms in the condensate. And as temperature drops down, the fraction increases. And when you are at, let's say, 1/10 of the critical temperature, that is at 10⁻⁸ Kelvin, 95 to 100% of the gas is, of the atoms are in the condensate. And on the right side, you see the first picture showing a condensate in rubidium atoms. I just flash it here, but I will comment and describe how this was made later on. I just want to show you here that this is a signature. This is a gas when the temperature, no, there is a big mistake here. It's the opposite. Here you are above T is larger than Tc. Here you reach the critical temperature, and here T is smaller than Tc. So make the correction on your note. You see when the condensate is obtained, all the atoms get in the center of the sample. The velocity becomes very small, well, it's much more diffuse. And you see here, the pedestal that you have here is the saturated gas, a gas which is not condensated. So I apologize for the mistake in ordering these three values. Now I want to finish with another problem which was raised about that time, again in the year 1923, 1924, which is the fact that you have other kind of atoms, which are called fermions, and which do not behave like bosons. They have the opposite property. The fermions do not like at all to be together. The bosons are, fermions are such that two fermions have to occupy different states. At most, you can have one fermion per possible quantum state. So if you have boxes with the same energy, you will distribute the boson, the fermions, at most with one in each state. This was hinted at. This was intuitively discovered by Pauli, and so that's what it's called often the Pauli exclusion principle. The fact that once you have one electron, for instance, in one state, another electron cannot come in the same state. And this has very deep consequences for atomic spectra, for chemistry, and so on. And this idea has been generalized then by Fermi and Dirac to what is called the Fermi-Dirac statistics, which is different from the Bose-Einstein one. And so I just finished by showing you how it works. What is the characteristic of the fermions? If you have to distribute fermions among states, you do exactly the same kind of start from the idea that you can order the energy, epsilon I. You have a degeneracy, you have GI, different states which have the same energy, GI, and you have to distribute the particles among these states. But now the formula that you use is no longer the one we used before, it is this one. GI is the number of states, which has to be larger than NI because you cannot put more than one state in each. And you have to use this formula, which I demonstrate on the next slide. Suppose that you have, what is a number of ways to choose n boxes out of an ensemble of G boxes. So you have G boxes and you have a smaller number of particles, but you have to put them into the G boxes. How many arrangements you have to do that? So here I give you an example with G equal 5 and N equals 3. So first of all, what is the number of ways to pick n boxes out of G? There are G ways to pick the first box. Then you have G minus way to pick the second one. Then you have G minus n plus 1 way to pick the nth one. So you have to multiply from G minus n plus 1 to G. And this is, of course, factorial G divided by factorial n. You just have the largest numbers product. This procedure counts many times the same configuration, since the order in which you pick the boxes does not count. So you have to divide this by G minus n, because this is the number of boxes, G minus n boxes that you have picked, okay? So finally, what you have to compute is the quantity which is written here. You take the log, you do exactly the same calculation as before, you get this expression. Then you minimize the free energy with, again, the Lagrange multiplier, which is the chemical potential. And you get, let you do the calculation, you get exactly the same result as for Bose condensation, except for a very small change. Instead of having -1, you get a +1 in the distribution. And this change of sign from -1 to +1 makes a big difference, as we will see, between bosons and fermions. So I just summarized on this slide the difference. For bosons, you have this formula with a negative chemical potential. And for fermions, you have this formula, just the -1 becomes a +1, and you have a positive chemical potential. What happens when T is equal to 0? When you go really down to 0, we have seen for bosons, all the particles go in the ground state, N0 goes to N, and all the excited particles, the number goes to 0. And for fermions, look at that. If you make T equals 0, so you have here something which goes to infinity. So it depends upon the sign of epsilon I minus mu. If epsilon I minus mu is positive, then these quantities goes to 0 because it's a positive exponential. So for epsilon I larger than mu, the number of atoms in the level I goes to 0. Now, on the other hand, if epsilon I minus mu is negative, then this quantity goes to 0 and n over gi goes to 1. So you see that all the states which have an energy smaller than the chemical potential are occupied, and all the states which have an energy above are unoccupied. And I show you at the bottom of the slide the difference. I assume an arbitrary distribution of states. You have a ground state, some excited states which are degenerate. In the Bose-Einstein Condensate, it's very simple. Everybody goes to the ground state. For fermions, it's quite different. Only one fermion per state up to the Fermi level. The chemical potential at T equals 0 is called the Fermi level. All the levels up to the Fermi levels are occupied, and there is nothing about. So you see a big difference. Electrons, and you have some atoms, some variety of atoms we see which behave like fermions, and some atoms which behave like bosons. And we will see the difference in a later lecture. Now, the last point I would like to make here is what I described up to now, the low temperature limit, T equals 0. Now take the other limit. What happens at high temperatures? And now it's very simple. At high temperatures, whether you have a -1 or a +1 sign here does not change anything. You tend towards this, which is just a Boltzmann distribution. So at high enough temperature, and by high enough, it means that KT has to be larger than the range of energies which are involved in the problem. At high temperatures, Bose-Einstein and Fermi-Dirac tends to Boltzmann. What does it mean? If you are at the Boltzmann, what does it mean, Boltzmann limit? It means that you can distinguish the particles. The way Boltzmann found his statistics was by counting by giving a name, an identity, a number to each particle. You can do that if the temperature is high enough. It doesn't make any difference because whether they are distinguishable or not, you get the same result. So this hints to something interesting. Quantum effects are effects which occur at low temperatures. If the temperature is large enough, asymptotically, you tend towards classical physics. So it's what I have written here. And now I conclude. I want to, with the last slide, to come to the conclusion. I think I have spent a lot of time here to show you how the ideas have evolved slowly during 1/4 century, from the first hint about quantum effects in 1900 up to 1925. Why did I stop in 1925? First of all, because I spoke a lot already, but second, because it's a good transition. This is the year 1925 when the mathematical formalism of quantum theory has been developed, and all what I have told to you fell in place in a consistent theory which explains everything I have discussed and even more phenomena. So it's very interesting to understand also that the concept of quanta has invaded physics. It not only involves the description of light, but also the atomic oscillation in solids, the energy spectra of atoms, and in all these phenomena, the Planck's constant, the same constant with the same value comes into place. Also, it's interesting to realize that the fact that you cannot distinguish between particles, whether they are photons or atoms, has very deep physical consequences. The notion of stimulated emission of light, the notion of Bose-Einstein condensation have announced phenomena which were discovered much later. Second idea, it became also progressively clear that these phenomena happen at low temperatures, quanta. And there is another example, another phenomenon that I alluded to without describing it, superconductivity, which was discovered in 1911, is also a quantum phenomenon which happens at very low temperatures. Now, also a big difference with relativity. Relativity is something which came from one very simple principle, and all the logical consequences have to follow. And so Einstein never doubted about relativity. On the other hand, the quantum ideas are much more diffuse. They did not come from a simple principle, and it was really, it emerged rather confusedly from very disparate observation in different domains. And we come to the point where the veil on the quanta will be lifted, and with one very, very big discovery, is the discovery by Louis de Broglie of matter waves. And it's again something that Einstein was involved in indirectly. Einstein did not discover matter waves, but he received the thesis of de Broglie, which was very controversial. Even the thesis director of de Broglie, Langevin, did not know what to do with that, and he sent it to Einstein. And like what Einstein thought about Bose, Einstein immediately understood that this idea, the idea of matter waves, was really important and was lifting the veil. And a few months later, Schrödinger discovered the equation which describes the evolution of matter waves. So, and immediately, the mystery were lifted. So I will start to describe this, describe the modern quantum theory next week. And I want to finish by one remark. I think it's absolutely remarkable that Einstein did most of his contribution to the quanta at the same time he was occupied by general relativity. So it's a really fantastic productivity period during which he made fantastic contribution to science in two very different areas. And he took it, the way he reacted to that was very different. He was very confident about relativity. And as we will see next week, he had very serious doubts about quantum theory, not about the facts that he discovered, not about the theories which were developed later, but he always thought that this was not the last word about the reality of the physical world. And I will discuss that during next week lectures. Okay, so I will stop at this point. Thank you for your attention.